Foundations of Amateur Radio. After recently talking about noise, today I want to discuss gain, specifically antenna gain. When you say that your antenna has 18 dBi gain, what does that mean? This entire discussion starts with an isotropic radiator or antenna. It's often described as the perfect antenna, but rarely is there any description on how that actually works, so I'd like to start there. Before we dig in too much, it's worth remembering that an isotropic antenna is a thought experiment. It cannot physically exist, but it's a useful tool for comparing antennas. Antennas have a physical size. There's often a direct relationship between the size of the antenna and the frequencies for which it works best. A lower frequency means a longer wavelength and corresponding large antenna to handle that radio frequency. In contrast, an isotropic antenna is infinitesimally small and responds equally well for all frequencies. Similarly, unlike an actual antenna, an isotropic antenna is symmetric in all directions. That is, there's no difference between the back or the front, the top or the bottom, the left or the right. You can position an isotropic antenna in any orientation, and there's no difference. Not just no detectable difference, no actual difference. The radiation pattern is a perfect sphere. As I said, the isotropic antenna is an imaginary, let's call it ideal antenna, that's used as the base reference to measure all antennas against. When you use the word gain in relation to an antenna, you're using the unit dBi, and in doing so you're comparing the antenna against this imaginary perfect isotropic antenna. When you see that the gain of an antenna is 2.15 dBi, you're saying that this antenna performs better than the isotropic antenna and does so by 2.15 dB. There's one minor detail missing in that statement. The full statement, often completely overlooked, is that this antenna performs better than the isotropic antenna and does so by 2.15 dB in some directions, but not all. Said differently, antenna gain comes from distorting the ideal perfect sphere into different shapes. For example, the 2.15 dBi gain of a horizontal dipole antenna distorts into a squashed donut on its side. In other words, there are directions where a dipole radiates better and has an increased gain when compared to an isotropic antenna. But there are also directions where it radiates worse, much worse, if at all. In the case of a dipole, it receives best from the side, and worst in line with the antenna, and I'll point out that the donut is also an idealized shape that in turn gets distorted by proximity to other objects, like the ground. Consider that a dipole has 2.15 dBi gain over an isotropic antenna. This means that for some directions the gain is increased, and for some directions it's decreased, perhaps even eliminated. In other words, in some direction the antenna amplifies the signal, and in other directions it attenuates the signal, potentially even to zero at a so-called null in an antenna radiation pattern. As I've said before, an antenna receives a combination of both wanted signal and unwanted noise. For an isotropic antenna, all signals, from any direction, both wanted and unwanted, are treated the same. This is not true for an antenna that has gain. Consider an antenna that exhibits gain in one specific direction and loss in all other directions. If you were to point that antenna at a wanted signal, the incoming signal would be amplified in that direction and attenuated in all other directions. If noise comes from all directions equally, most of the noise would be attenuated, and only a little bit of noise coming from the same direction as the wanted signal is amplified. Overall, this means that the total amount of incoming noise is reduced in comparison to the wanted signal. In other words, the noise floor is reduced, and the signal level is increased, making the signal more audible above the noise. This means that the impact of antenna gain is that the signal-to-noise ratio is improved for an incoming signal in comparison to local noise. Notice also that the antenna gain works in multiple ways. It serves to improve the local signal-to-noise ratio by attenuating noise and amplifying a wanted signal, but it also increases the transmitted signal that's sent towards the other station. Both affect your station's performance, but do so at different sides of the communication link. And because we're talking about two separate signals, an incoming one and an outgoing one, the optimal direction might not be the same for both. So, Now what do you think the impact might be of adding an 18 dBi Yagi to your station? I also have a supplementary question. If a commercial antenna is compared with the dipole using the dBd unit, is the antenna compared to the entire radiation pattern of a dipole, and if so, at what height from what type of ground? And is that a useful comparison, or hiding the true performance of such an antenna? I'm Onno, Victor Kilo 6, Foxtrot Lima, Alpha Bravo.